Section 3.5, Rate of Change. In example 1, we have a construction crew resurfacing part of the highway. They began on May 5th at mile marker 136, and on May 21st they had completed through mile marker 152. Find the average rate at which the project was being completed. The average rate is going to be a type of slope, and so we need to figure out what we want to be our independent variable and our dependent variable so we can compute the ratio correctly. One of the ways to think about that is, do we want to talk about miles per day or days per mile? Since we're expecting them to pave more than 1 mile per day, the unit of miles per day is going to make the most sense. Remembering that per is a division word, we want to compute the number of miles, then divide by the number of days. So to compute the number of miles, we're going to subtract. They ended with mile marker 152. They started at mile marker 136, so if I take that difference, it'll tell me how many miles they completed. And to find out how many days it took, we're going to take the difference of the dates since they're both in the same month. The 21st was the ending date, minus the 5th was the starting date, to get our number of days. 152 minus 136 is 16, and 21 minus 5 is 16. 16 divided by 16 gives us 1. So the average rate at which the project is being completed is 1 mile per day. Since per is a division word, you can also use the slash to indicate per, so 1 mile slash day would read as 1 mile per day. Let's look at the next example. The percent of babies born to unmarried women in the United States has been increasing approximately linearly from 10.7% in 1970 to 40.8% in 2010. Find the average rate at which the percent of babies born is increasing with respect to time. So I want the percentage with respect to, or per, time, which is going to be my year. So I know that I want my units to be the percentage per year. So I'm going to set my percentage up on top of the division and my time, my year, up on the bottom of the division. The change, we always want to compute our change with the final amount minus the initial amount. So 40.8 minus 10.7. For the change in percent over the change in year, to find out how many years it's been, we can subtract 2010 minus 1970. If we subtract the percentage values in the numerator, we'll get 30.1. And if we subtract the years in the denominator, we get 40. Finishing the division gives us 0.7525, and the units on this are percent per year. So the percentage of babies born to unmarried women is increasing by 0.75% per year. As we saw above, rate of change is computed by measuring the change in y minus the change in x, or y2 minus y1 over x2 minus x1. This formula looks familiar because this is the same formula we use to compute the slope between two ordered pairs. The rate of change is a slope. The difference between talking about rate of change and just talking about slope would be that slope is usually between ordered pairs, does not have units, whereas in a rate of change situation, it's going to be a problem that's worded in such a way that the units are going to be important. In January, the sea ice extent for the northern hemisphere increased approximately linearly from 15.5 million square kilometers in 1979 to 13.6 million square kilometers in 2006. I'm going to write this as ordered pairs and find the average rate of change. Now when I write my ordered pairs, it depends what my independent and dependent variables are. The independent variable is going to be the year, and the dependent variable is going to be the amount of ice. So our ordered pairs should be in the form of year, comma, ice. Independent variables are always first in the ordered pair, and dependent variables are second. So the first ordered pair would be 1979, comma, 15.5, and the second ordered pair would be 2006, comma, 13.6. Now it is unusual to have a value so large as 1,979 in an ordered pair. Oftentimes we have a starting year, and we measure our year as t years since a starting year. If no starting year is given, we can make up a starting year, or it is possible to use the original year. Let's make up a starting year and verify that we get the same rate of change. So if I just make up the starting year of 1980, 1979 would be -1 year since 1980, since it was before, and 2006 would be 26 years after 1980. So let's compute the average rate of change first with the original values, the year in there. The average rate of change is going to be 13.6 minus 15.5 divided by 2006 minus 1979. That gives us -1.9 over 27. If I divide those into a decimal, I get -0.07037 approximately. Now let's go ahead and do the same computation with a starting year of 1980. We'll start with our 13.6 minus 15.5 over 26 minus -1. As you can see, when we complete our subtraction, we're going to get the -1.9 over 27 again. That's why we're able to choose any year we would like to use as a starting year and shorten our numbers down. This is especially important if we're going to be graphing or writing an equation using this data. Last, let's go ahead and stick our units on here. The units on the top of this fraction were the units for the ice, so they're going to be million square kilometers per year. On to the next page. Example 4, a person who is 132.5 centimeters tall should use a ski pole that is 90 centimeters long. A person who is 153 centimeters tall should use a ski pole that is 110 centimeters long. Find the average rate of change of the length of the ski pole with respect to height. First, we need to decide what the independent and dependent variables are. The length of your ski pole is going to depend on your height. So we're going to have independent being your height and dependent being your pole length. Dependent variables are the y variables and independent variables are the x variables. So the ordered pairs are going to look like 132.5, 90 and 153, 110. So the average rate of change is going to be 110 minus 90 on the numerator divided by 153 minus 132.5 in the denominator. When we complete the subtraction, we get 20 on the top divided by 20.5 on the bottom. That gives us about 0.9756. And because the units on both of these are centimeters, we're going to want to write out our units in a sentence. A person's ski pole should be 0.9756 centimeters long for every centimeter of height. So the units are centimeters long per centimeters tall. In example 5, D is the distance in miles that a student can drive in T hours. We've got a table here and we want to draw a scattergram first. After looking at the values of T and D, it becomes apparent that a good scaling for T would increment by 1 and a good scaling for D is going to increment by 30. Draw your points and connect them with a straight line. Now we want to find the slope of the model. To find the slope of the model, we can find any 2 points and calculate the slope. So let's go ahead and use 0, 0 and 2, 120. So slope, or m, is equal to 120 minus 0 divided by 2 minus 0. So 120 divided by 2, which is 60. Now you can find this in the graph as well by counting rise over run. But be careful that when you count rise over run, you count each of these blocks right here as 30 since the scaling goes up by 30 on the y-axis. So it's 30, 60 over 1 since the scaling on t is 1. What does the slope mean in this situation? The units on D were in miles, the units on T are in hours. So it means that the student is driving at 60 miles per hour. Putting the units back onto that slope makes it a rate of change. If there is a linear relationship between two values, T and P, then the rate of change of P with respect to T is constant. Vice versa, If the rate of change is constant, it's going to be a linear relationship. It means that no matter what 2 points you choose in a line, you'll always get the same slope. And this is only true of lines, not other types of relationships. If we look at example 6, a person earns a starting salary of $30,000 at a company, and each year she receives a $2,000 raise. We can interpret those values as part of an equation. The $2,000 raise or increase that she gets each year is going to be the slope of a linear model. When 2 is the slope value, it means that her salary increases by $2,000 per year. What is the s-intercept? I know that the s-intercept is going to start with 0, comma, some value. This 0 is going to refer to the starting year, the year that is 0 years since some initial year. So since we're looking for the starting value to fill in the rest of this ordered pair, we look for her starting salary, which is $30,000. What this means is initially, her salary is $30,000. Now we want to find an equation of the model. To write a linear equation, we just need these two pieces, slope and y-intercept. So the equation of the model is going to be y equals 2x plus 30. But x and y are so generic, we want to use better letters. We want to use the letters t for year and s for salary. So let's change that to s, salary, equals 2t plus 30. Remembering that year was our independent value, our x value, so we're going to replace x with t. And salary was our dependent value, our y value, so we replaced y with s. Let's perform a unit analysis on the equation. The units on salary are thousands of dollars. The units on the 2 are thousands of dollars per year. The units on t are years. And the units on 30 are thousands of dollars. When I multiply the 2 and the t, year and year cancel, so that gives me thousands of dollars plus thousands of dollars equal thousands of dollars. So the unit analysis checks out. Let's look at the next example. Let T be the 1 semester cost of tuition for B billing contact hours for classes at JCC. So we've got a table here of the cost of tuition per contact hour. And a note below that student fees are usually $35 per billing contact. We want to find a linear model for a Jackson County resident. The first thing to do is to consider what the slope would be. So both of these quantities have to do with billing contact hour. So the slope is going to be a combination of the 117 and the 35. Y-intercept is going to be the ordered pair 0, 0 because there is no initial cost. All costs that are given here depend on contact hours. So our equation might start off y equals 152 x plus 0, and then we will change that in terms of the variables in this problem. The variables in this problem are going to be t and b. T, this is the tuition cost, b is billing contact hours, so t is the dependent variable and b is the independent variable. Next, we'll find a linear equation for an out-of-state or international student. The out-of-state or international student is going to pay $234 per credit plus the $35 per credit. And they will also have 0, 0 as their y-intercept. So their equation would be t equals 269 b plus 0. What is the cost of tuition for 1 semester, including 15 billing contact hours for a Jackson County resident? So we're going to plug in 15 for b. That's 152 times 15. We get 2,280. So it costs a Jackson County resident $2,280 for 15 billing contact hours. What about for an out-of-state student? For the out-of-state student, the amount of tuition is going to be 269 times 15, which gives us 4,035. So it costs the out-of-state student $4,035 for 15 billing contact hours. Example 8. Let n be the number of multiple organ transplants in the year that is t years since 2000. We've got a table here and a model given below. What is the slope of the model and what does it mean? So the slope of the model we can see is going to be 64.7 since that's the coefficient of t. To figure out what it means, we need to check out the units on both our independent and dependent variables. The units on the dependent variable are number of multiple organ transplants, and the number on the independent are years since 2000. So the slope means that there are 64.7 multiple organ transplants per year. In Part B, we're going to use the data to find the slopes between the ordered pairs and compare them to our answer from Part A. So let's go ahead and start with 2001 and 2002. Let's calculate that slope. So we're going to have 338 minus 245 divided by 2 minus 1. Since 2002 is 2 years since 2000 and 2001 is 1 year since 2000. So this gives us 93 over 1, or 93. Now 93 as a slope is much different from 64.7, so let's keep going to see if we can figure out what's going on here. Let's find the slope between 2002 and 2003. So we've got 360 minus 338 over 3 minus 2. That's 22 over 1, or 22. Way different from 93, still way different from 64. Let's keep looking at different pairs here. Let's look at between 2003 and 2004. We're going to have 448 minus 360 over 4 minus 3. That gives us 88 over 1, or 88. We'll look at between 2004 and 2005. That gives us 532 minus 448 over 5 minus 4. That gives us 84. And for the last one, 2005 to 2006 gives us 564 minus 532 over 6 minus 5, which gives us 32. So if we look at all of these slope values, none of them are 64.7, none of them are particularly close to 64.7, but 64.7 does kind of fit in the middle between them. This is showing us that our data, if we graphed it, our data is not going to be an exact linear relationship. It's an approximate linear relationship, and if I connected those lines with the line that fit the center was going to have a slope of around 64.7. We'll talk more about how to find this value, the 64.7, when we talk about linear regression in the next chapter. What is the n-intercept and what does it mean in this situation? The n-intercept of the model is 188. So 0, 188 is my ordered pair. It means that initially in the 0th year, which is the year 2000, there were 188 multiple organ transplants. Next, we want to use the model to predict the number of multiple organ transplants to be performed in 2010. So for 2010, we're going to plug in a t-value of 10 years since 2000. So we'll have n equals 64.7 times 10 plus 188. So we predict that there will be 835 multiple organ transplants in 2010. Let's look at the next example. Fill in the following tables for the three linear equations. If x is 0, y is negative 7. If x is 5 divided into 5 one time gives me 3 minus 7, negative 4. If x is 10, gives me 2 times 3 is 6, minus 7 is negative 1. And if x is 15 divided by 5 is 3, times 3 is 9, minus 7 is 2. Go ahead and complete the remaining two charts. Notice that in the tables, since these are linear equations, there's going to be a constant increase or decrease in the x and y values. These x values increase by 5 each time, and their y values increase by 3 each time. The ratio of those is 3/5, which is the slope. These x values increase by 2 each time, and these values decrease by 1 each time. Again, their ratio is the slope. These values increase by 1 each time. These values increase by 3. The y values increase by 3 each time. And the ratio is the slope. So you can tell from looking at a table if you have a linear equation or not if the ratios are consistent. Always the same on x means always the same on y. So let's decide whether or not there's a linear relationship between these data points. So the change in x is an increase by 4 each time. The change in y is a decrease by 3 each time. So this is linear. And furthermore, we can say that the slope has got to be negative 3/4. In the next table, we have an increase of 3 on x. The first increase on y is 2. The second is a decrease of 5. And the third is an increase of 7. This is not linear. Our fourth table has an increase of 1 on x. The first y increases by 5, the second y increases by 4, and the third y increases by 5. This is not linear because they're not all the same, but it is close to linear. It would not be an exact line, but we could use a linear approximation. If we're given a table of a linear equation, we can fill in the rest of the chart by figuring out what the slope is going to be. These have an increase of 1 on x and an increase of 5 on y, so the slope must be 5 over 1, or 5. That means that each time x increases by 1, y has to increase by 5. So the next value must be 13. If x increases by 1 again, the y value must increase by 5 again. So the next value has to be 18. And so on. The value corresponding with 4 has to be 23. In this chart, when I increase between 20 and 24, I have an increase of 3. And on y, I have an increase of 6. So the slope must be 6/3, or 2. Since 2 is 2 over 1, it means if I have an increase of 1, I must go up by 2. So that would give me 27. An increase of 1 up by 2, 29. An increase of 1 again, up by 2 to 31. So that matches, that works with the pattern. And an increase of 1 would put us at 33. So by calculating the slope, we can fill in the rest of the information for this linear data set. And that's it for this section.